A lifetime spent teleoperating robots is going to be a drop in the bucket compared to what you need to really learn how to generalize. So you're spending a lot of money on what we believe is a dead end. There is no reason to think that we're going to do a teaching reality with anything short of an internet's worth of retraining, followed by some level of fine-tuning. If you could have AI in the physical world, that would not just transform industries and factory automation, but it would really transform the way the global economy works. But the problem with that is today's models don't work well in the real world. And so the way we train our model is using what we call a data pyramid. As you go up the pyramid, you get more and more task-specific data. But what we learn is that the models that tend to perform best are the ones that have less curated data.
You're one of the few founders in physical AI that has scaled through many different cycles. So for the first-time founders listening, what are most founders overweighting versus underweighting when they're building in today's world?
I think there are probably two pieces of advice I'd give. The first is
Hey climbers, welcome back to this episode of Climb by VSC. My name is Jay Kapoor, General Partner of VSC Ventures, and I'll be your host today. We talk about on this show every week how AI is changing the things we build and back. But what about the things that build the things? And so today I'm excited to talk about the world of physical AI with a builder who has taken multiple companies from foundation to exit successfully in many eras of deep tech. Today I'm joined by Jagdeep Singh, who is the founder and CEO of Rhoda. Rhoda is taking a very unique approach to training robots to operate in real customer tasks in the real world, not through tens and thousands of hours of real teleoperations training, but through just 10 to 20 hours of YouTube videos. It's such a fascinating paradigm because it takes down the amount of time to not only train a model, but also to deploy it in the real world. Jagdeep is one of these founders who is happy to share his experience with us, not just in how you take a POC all the way to scale, but also in what the right approaches need to be, how you raise capital for those approaches, and the biggest mistakes that deep tech founders make when they start a company to build for the long run. I am so thrilled to have him on the show today. Jagdeep, thank you so much for joining me.
Pleasure to be here. Thanks for having me, Jay.
So many different places I want to take this conversation. I want to start with what you saw. So you have built multiple companies before. You've built and scaled these companies across three different deep tech frontiers, optical networking with Infinera, solid state batteries with QuantumScape, and now with robotic intelligence at Rhoda. Each time I felt like you were making a bet against what the market was saying on the fundamental physics. So let's start there. What did you see with Rhoda that made you feel like this business needed to exist?
It starts with an observation that AI is changing everything. Right, and over the next 10 years, I think the society we live in is going to be fundamentally different because of AI. Given that, of course, you kind of want to be in AI because it's changing everything. Having said that, the impact of AI so far has been limited to what I call the symbolic domain. So this is basically where you're working on bits and symbols, not bits and not atoms, essentially. So we've seen language models, for example, make a huge impact. They can write text, they can write code. We've seen image generation models, we've seen video generation models, deep fakes, for example. These are amazing developments. However, the ability of AI tools or AI models to manipulate atoms is effectively zero right now, in the sense that the number of deployed intelligent robots that are capable of manipulation in the real world is close to zero. You have robots that are doing things like locomotion, and things like inspection and monitoring applications. People have, network models running on quadrupeds to do those applications. But as far as applications that involve working with hands and arms, manipulation, AI has not made an impact. And the question that we were asking ourselves is, why is this the case? It's clear that if you could have AI manipulate objects, you could make a massive impact not only on toy tasks, but you could change the way the global economy works. All of production really is done today in a way that requires human beings. In today's automation that exists, that has been around for many decades, is largely point-to-point automation. So if you could have AI in the physical world, that would not just transform industries and factory automation, but it would really transform the way the global economy works. It's a massive change. But the problem with that is today's models don't work well in the real world. You've probably seen lots of robots doing cool things on videos, right?
Sure,
on
yeah.
the
Boston
internet.
Dynamics had
Yeah.
all of these viral
You-
videos
you,
of.
you can do backflips. You can do things like even fold T-shirts to make coffee. It turns out that all of those demonstrations are really in a lab setting.
Yeah.
And the problem with the lab setting is that you can basically you can stage it to where the scenario you're testing matches very closely the data set the model was trained on.
You give the robot the answer to the test.
Pretty much, right? Exactly. You've pre-trained on exactly what you're going to test it on, right?
Yeah.
Unfortunately, the real world doesn't work that way, right? In the real world, the distribution of data is much broader. There's a much longer tail of rare events, basically corner cases that lead to failure, and you can't help that. The distribution is different. What you need is a model that's capable of dealing with that distribution.
Yeah.
That's a problem that we saw, and it was a big enough problem to where we thought there was an opportunity here to really change the world.
Yeah. So your Gen Zero model, your prototype, you're building your model on existing hardware, partner hardware. But longer term, the vision is to bring your next model onto your own design. So talk to me about how you phase that. Should I think about it like the Android model for phones, where this is something that could run eventually on any machine? Or is the long-term thing to be fully vertically integrated, and how do you get there?
Yeah, so the way to think about it is that we want to build the best solutions for our customers. Those solutions require a full stack solution. They require an AI model, they require hardware. Neither one of those really exists in the form that we want it to exist in, so we're doing both. Having said that, the critical unsolved piece is the AI model. So we're an AI first company because of all the points I made earlier. The model needs to be able to be robust enough to work in the real world, and that's an unsolved problem.
Yep.
We believe we're actually addressing it here, but until the DVA, we really haven't seen models that are capable of crossing the chasm between the lab and the real world. That model is in pretty good shape in terms of maturity, and there's no reason for us to wait until we have our own hardware to make that model available to our customers. So what we're doing is running that model on off-the-shelf hardware.
Yep.
The robots you see here, for example, are off-the-shelf commercially available robots. But with our model, they can do many more useful things than they would be able to do without the model.
Yep.
Now, having said all that, with our own hardware, the models can do even more, right? Because we also can't find good enough hardware to do all the tasks that we have in mind. So the way to think about it is that the model is in fact the key value creation of the company.
Yep.
These models can work on any hardware platform. We're hardware agnostic. We've already run the model on multiple different hardware types already. That allows the model to perform a wide range of industrial and commercial tasks. With our own hardware, we simply increase the level of sophistication of the tasks we can perform.
Yeah.
Right? And so over time, we see the model getting more and more powerful, and together with the hardware, doing more and more interesting tasks.
Yeah. Let's talk about capital intensity, because building your own full stack solution necessitates an amount of capital that you and many other players in the category have raised. So just to get the numbers right, Physical Intelligence has raised 1.1 billion, Skilled has raised 1.5, Figure 2.3, maybe more now, and you've recently announced a raise of 450 million. In AI software, we saw that training frontier models was a capital expenditure game. People were putting more money into it, and the models were getting better over time. In physical AI, is that the same arms race, or should we be thinking about capital to physical AI model maybe a little differently?
So first of all, the physical AI models are not nearly as big as the models that we see in the language model space.
Yeah.
So you don't need the same level of compute to train those models. Having said that, the companies you mentioned are all doing what are known as VLAs, the Vision Language Action Paradigm. Remember, in the VLA paradigm, you start with a language model, and you post-train it on some teleoperation data collected by teleoperating robots or puppeteering robots around. And the idea is you run the robot through certain trajectories, doing certain tasks like making coffee or folding T-shirts. And when you collect enough such trajectories, you train the model on it. This approach has a couple of problems. One is, to your point about capital intensity, you need an enormous amount of capital to collect this teleoperation data, right? And that's where a lot of the capital these companies are raising is going, is teleoperation. Unfortunately, in our view, a lifetime spent teleoperating robots is not going to be enough. It's going to be a drop in the bucket compared to what you need to really learn how to generalize, to learn a strong prior on physics. So we think this has a double problem, which one is that it's expensive to collect teleoperation data. But secondly, and even more severely, you can never collect the scale or the diversity of data required to truly generalize. So you're spending a lot of money on what we believe is a dead end path, basically. What we're doing is something different, right? We ask ourselves, what source of data is there that has the scale, the diversity, and the ability to learn physics that's already out there, right? That we don't have to generate on our own.
Yep.
And there's only one possible answer. That's internet video, right? By some estimates, something like 80% of all the data on the internet is video. These videos cover virtually every conceivable scenario, from human beings doing crazy things to scenes where there are not even any humans present, like the canonical example we use is waves crashing on a beach. Even those scenes with no humans in them have something to teach the model about the physics of how the world works. And so the way we train our model is using what we call a data pyramid. The bottom of that pyramid is very general data, of which there's a lot, right? Maybe not even having a human in the scene. And then as you go up the pyramid, you get more and more task-specific data, culminating in the end in maybe a video of an actual human doing the actual task you want it to do. But what we learned, kind of a bit counterintuitively, is that the models that tend to perform best in our experience are the ones that have less curated data. Because the less curated data, turns out, forces the model to learn more about how the world works. And once you have that prior, you can apply that prior on a given specific task. And this is, of course, what leads to the incredibly high data efficiency that we announced in our launch a couple of weeks ago. We can train models to perform very sophisticated tasks, like, for example, this task, which is an automotive decanting task. These boxes are full of ball bearings. And as we showed on the internet with our videos, the robot's able to open the box. Well, first of all, lift the box. It's a 10 kilograms, a 22-pound box. Able to lift this box, pull open the little pull tab, which is a dexterous action, pop open the lid, open the plastic bag inside, pull out some desiccant paper, put it in the trash, dump the contents. Do all that, with on the order of 10 to 20 hours of robot data. So in our view, that's really a high watermark, maybe a low watermark for how much data is required. And all that is enabled because the model has actually already been trained on hundreds of millions of videos. So it's learned a really strong prior on how things move. Without that, you would have to collect tens of thousands of hours of data. And even then, as we see with VLA models, you can only do the task if you recreate exactly the data set that it was trained on.
Yeah, so I want to come back to the 10 hours piece in a second, because that's a very interesting claim, especially compared to the number of hours some of these VLA companies need.
It's not a claim, it's a fact.
Right. So that's what I mean. The ability to do it with 10 hours and the fact that you've been able to do it with 10 hours, I think is something I want to really spend more time on. Before we do that, you started talking about teleoperations being kind of one of the things. It's not the only way that these models are being trained.
Correct.
Right? So the hierarchy, as I understand, there's teleoperations, there's synthetic data, there's world models, and then obviously it's the DBA method that you're talking about. Maybe lay the landscape a little bit of where these play in and where you fit in that paradigm.
Yeah, so there's a few main approaches to collecting data. We talked a lot already about teleoperation, right? This is, again, where you have a human being puppeteering the robot to perform certain tasks. Like, think of it as remote control, right?
Yes.
And then as the robot's performing those tasks, you're collecting that data, and you'll assemble that data into a large data set that you post-train the robot on, the model on. A different approach, and the downsides of teleoperation are, one is it's expensive to collect data, but more fundamentally, the size and the diversity of those data sets is always going to be limited, because you're only collecting data that you've intentionally collected. You're not seeing, almost by definition, the things that are unintentional, because that's data.
You would never test the edge cases. You're only testing exactly what needs to be done.
Any edge case you test is by definition, you're testing for that specific edge case, not all the other infinite number of ways that things can kind of go wrong, right? So that's, in our view, a very serious problem with teleoperation, and this is why we think teleoperation is not going to lead. Teleoperation alone is not going to lead to true generalization. Right? The second approach is, of course, simulation. People say, well, why? What if you didn't have to use real robots? What if you could run robots in simulation and use the power of computation to get a lot more data? And the answer there is you probably could get more data that way because you're not dealing with physical atoms. However, you have the exact same problem with diversity. You're collecting data that you intentionally collect, And diversity, it turns out, is an even bigger issue with generalization, preventing generalization than pure scale alone. And that's ignoring the whole sim to real gap, which is the idea that even with all the years of experience we've had at simulation, you really can't capture the full richness of the real world in a simulation. But ignore that for a second. Just the diversity alone is kind of a fatal flaw. Yeah. Another approach people are using is synthetic data, where you can actually use like a video model to generate scenes and so on. The problem with that is in fact synthetic. So any mistakes the model makes relative to how the real world works in terms of physics are going to be in the model that the model it learns from. So all of these approaches have, in our view, some serious drawbacks. And the only approach that we think really meets the three requirements of internet scale, internet diversity, and the ability to learn real physics is internet video, right? So we keep falling back to that. That's really, it's really the only way to get to the kind of scale we're looking for. One analogy I want to point out is that this approach isn't actually, it may be radical in the robot space, but it's not that radical at all in the AI space. Okay. Every generalist AI model that you use every day, things like language models or image models or video models, these are trained in exactly the same way. The pre-training phase involves tens of trillions of tokens from that domain, basically an entire internet's worth of data. So the combined output of all of humanity in a given field, whether it's text for language models or images for video image models or video for video models. And then a small amount of post-training on a data set that's aligned very closely to what you want the model to produce. That's called fine-tuning. The combination of massive internet scale pre-training and a small amount of fine-tuning is what's produced generality everywhere else. There is no reason to think that the robotic space is any different than any other space. There's no reason to think it's going to require, that we're going to be able to achieve generality with anything short of an internet's worth of pre-training, followed by some level of fine-tuning. And if you need an internet's worth of data, there's only one source that exists, and that's internet video.
And how do you think about defensibility of that, given that this is publicly available stuff, right? And so, in one hand, I think about where value accrues. NVIDIA is a good example of this. They made all of this investment in the picks and shovels, and then the value accrued to the inference layer and the application layer. Is the same thing going to happen in physical AI? Are there going to be moats in what you're doing?
So there are two things that I think are moats comes down to what's difficult about this problem. What's hard for people to replicate, right? And there are two things. One is basically, yes, the data itself is accessible. It's available. That's how we access it. But in order to actually be able to harness that data and be able to ingest it, you need a whole set of techniques that are not typically used in the world of robot learning. These are techniques that come from the world of computer vision and generative AI. And what they require is that you understand physics to a high level of accuracy, and you can reproduce the physics in real time. So we need to make video predictions of what's going to happen that are both physically accurate, they don't involve hallucinations, and they have to happen in real time, in a few hundred milliseconds. We're not aware of another video model that can make video predictions that are that accurate and real time. Ordinarily, those two things are run at cross purposes. To make a model more accurate, typically you make it bigger. If you make it bigger, it runs slower, not faster. How do you make a model both more accurate and faster? That's the central sort of challenge that our team has figured out how to do because of their backgrounds, computer vision and generative modeling. That's just the first layer of the moat, though. That allows us to get the model to be good enough to where it can run autonomously in real factories. Now, once you're running autonomously in real factories, now you're starting to see all the corner cases that I talked about, all the edge scenarios. And as you deal with those edge scenarios using a technique called Dagger, you're now getting data on the long tail of the distribution, and that data is proprietary. Right? That's not available on the internet. Only a robot that's already autonomous and operating will be able to collect that kind of data. And using that data makes a model more robust, which then allows us to deploy it more and collect more data, and it kicks off this classic data flywheel. So that's a much harder moat for people to replicate. The first moat relative to the techniques to process video in a way that's both real-time and physically accurate, with the right talent and enough time, you could probably see people replicating that. But by then, certainly our plan is to have enough deployments to where we start collecting these long tail data points,
Yep.
And that makes the model really robust. And at some point, it really, in our view, is a winner-take-all kind of a scenario, because the model that gets good enough to see more of these corner cases is the only model people want to deploy. But the model that people want to deploy is the one that gets more data to make it even more robust. And then you just kick off this
So
cycle.
said another way, you are unlocking deployment by using the DVA model. You're able to get the model to a point where somebody would want to live deploy it, and the more live deployments you have, the more you can strengthen the model.
You said it much better than I did. I see now why you're a storyteller.
A bit of what I do for a living.
Yeah.
So let's talk about this 10-hour data point that you mentioned here, which is so interesting, especially given how much of the industry focuses on teleoperations, the number of hours. You'll see these claims from the industry where they'll say, with 10,000 hours of training, we were able to do this. With 5,000 hours of training. And you just said to me, it takes 10, maybe 20 hours to be able to confidently do this task. Help me square how you get to that low number.
I'm really glad you brought this point up, because this is actually really one of the most interesting things about the Rhoda story. If you look at the evolution of VLAs over the past few years, you'll see claims relative to how much data they were trained on. So you'll see some people claim that we trained on 70,000 hours of robot data. Then you'll see the next guy saying we trained on 270,000 hours of UMI collected data. UMI is a type of collection data, and so on. Or some people saying 500,000 hours. And then you come to Rhoda, which is later in time, and we say we train on 10 to 20 hours of data. And it's like, it's almost like, well, wait a minute, why are you not in this game of trying to increase the number of robot hours? And the answer is because that game, it just doesn't lead to generality. No matter how many hundreds of thousands of hours you collect, right? It just pales in comparison to the amount of data and diversity you need to really understand how the world works. And so we kind of changed the rules of the game. Our approach was, let's try and learn fundamental physics from an internet scale data set that already exists, and that's internet video. And if we succeed at learning a good prior, then we should in principle be able to learn specific tasks with a very small amount of data. To be candid, we surprised ourselves by how little data we needed. We didn't think 10 to 20 hours would be a reasonable target, but that's what we're seeing. We now run multiple POCs at real factory settings. By factory settings, I mean we're dealing with all of the complexity that happens in real factory. This particular setup here was run in a live factory. By live factory, I mean they're processing real material flow through the factory into real cars. By definition, that means you're not controlling it. It's not staged for a lab. You're dealing with the boxes and the straps and the parts as they're coming through the material flow pipeline. And the fact that we could do that with that little amount of data collected really was really gratifying. It confirmed for us that the basic idea of pre-training on a massive internet data set to learn a strong prior and then fine-tuning with a small amount of robot data is in fact a really good strategy.
The error correction piece you mentioned a little bit earlier, I'd love to understand that a little bit better, where you're saying it's running a prediction in real time of what should be happening, and then every, whatever it is, 100 milliseconds, course correcting. Is that different from how typical VLA-based approaches go, or is that something unique to what Rhoda's doing?
So every VLA approach has to make a prediction of what the robot should do next. But what they're doing is predicting actions, and those actions are not based on a video-based prediction, right? So they're trying to learn how to make a prediction of what should happen next based on this limited number of hours of robot data. So remember again, with the VLA, the pre-training is entirely language and image-based. There's no knowledge of how things move in the pre-training. So all of the motion prior, all the motion understanding the model has, the VLAs have, comes from that teleop data set. And there just isn't enough data there for the model to really learn how things work. And you're asking the model to make a general prediction of what should happen next based on a very limited data set.
And the variance in those predictions could be anywhere because you just don't have the right amount of data to do it.
Exactly. It's just, you're not going to be able to make a good prediction because you just haven't seen it. You can make a good prediction if the scenario matches close to what you've seen before. But as things start to diverge and you haven't seen it, once the model goes out of distribution, right? The output is random. There's no way for it to come back in distribution again. And the beauty of having pre-trained on hundreds of millions of videos is a model that's seen so much that it always has a fallback. Even if you do something that wasn't seen in the 10 or 20 hours, it's seen enough other stuff that's similar to where it can make an intelligent prediction of what should happen. I'll give you one simple example of this that to us was the moment that we felt like, this thing is going to happen for real. This is not just a lab experiment. We were in the factory at this automotive customer, and we were showing one of their top executives this particular task working, and the robot was picking up boxes and boxing them. And the executive came up and was a bit skeptical, and he picked up a glove that was lying nearby and threw it in there. Now, we had never trained this model on picking up a glove out of the box, and we're like, whoa, what's this thing going to do? So it saw the glove, it reached in, picked up the glove. Another question is, which trash can did it put it in? There's a trash can for cardboard recyclables, a trash can for plastic bag recyclables, and a trash can for just regular trash. And it put it in the regular trash can because it wasn't a cardboard box and it wasn't a plastic bag. This guy was unconvinced. He picked up the glove again, put it into a plastic bag, and threw that into the container. And we're like, okay, now
now you're really trying to break it.
Yeah, and we were like, hey, this is not something the model was trained to do, so I don't think it's going to. What the model did was it picked up the plastic bag, grabbed it from the ends, shook out the glove, threw the plastic bag into plastic recycling, then picked up the glove and put that in the trash.
Wow.
At that point, I was like, man, we've never trained it on a task this far out of distribution. How did it figure out what to do? And that's where we thought, okay, this pre-training is definitely having an effect. And it really was very exciting for us.
So the generalization piece, this is the tension that I am hearing, and I hear from a lot of the robotics industry. You are talking about building for generalization, but so far we've really talked about very specific tasks, right? So you're talking about a specific decanting task. I'm sure eventually you would move on to other tasks. How does the tension between the story you're telling investors, which is this is a path to generalization, versus what the customer wants, which is very specific tasks, how do you marry the two?
There really isn't any dichotomy there. I mean, think of human beings. This task is currently being done by human beings. Those human beings are not specialists. They have the same kind of brain that you and I have, the same kind of limbs and embodiment that you and I have, but they're just doing a very specific task, right? That's the way we think of a model. The model itself is a generalist model running on generalist hardware. Right? We are not customizing it for any one given task. Where the specialization comes from is the post-training. In the same way that you hire a worker and you would train them on how your specific company does a process. You hire this generalist model and you train it on how your company does that process. And over time, of course, unlike a worker, the model can learn more and more different tasks to the point where it can actually have a chance of operating zero shot, which means without any training at all. Again, that is something that we're trying to do right now because we're just focused on solving real cases. Our goal right now is to get that data flywheel going, which is to deploy enough real-world robots with our models to where we can start seeing more and more of these corner cases and make the model more and more robust. But over time, our belief is that the amount of task-specific data you need gets lower and lower to the point where eventually you don't need it at all.
So I want to talk about scaling because obviously the POC, very impressive. You convinced a skeptical executive. You've got a few of these in deployment where you're collecting some real world data. But even just within this specific use case, how do you go from 5 to 1,000 to 10,000 so you're able to collect data at the scale you need to really solidify your position?
Yeah, so I think there's a few key elements of scaling. The first is it has to be demand. On the demand side, this is about as scalable an application or a use case as you can get because virtually every business has some variant of this task. Every business receives incoming materials in boxes or containers. Those materials have to be decanted or taken out of the boxes, processed, and then shipped out again. So if we do this task here, we can train for its variants at places like Amazon and anywhere else that materials are processed. The second thing you need hardware that's capable of doing the task. And right now what we're finding is these off-the-shelf robot arms that have 7 degrees of freedom can handle 10 kilograms per arm, have impedance control, so they have torque sensors so they can detect how much force they're exerting, are more than adequate to do these tasks. And because they're off the shelf, we can just place orders for them and get deliveries. So we don't have to. There's no short-term bottleneck in terms of getting supply. The third thing, of course, you need is the AI model itself. Probably the most important thing. That's the part that has never existed before. And that we are really excited about for all the reasons we've already been talking about. And the final thing you need is the software that pulls everything together, the bridge software, so to speak, that gets data from the sensors, sends the data up to the model, gets the data back from the model and uses it to control the actuators and so on. And those are all the things that we're currently working on. All these four things all require work to be done.
Yeah.
But none of that work, in our view, is rocket science that hasn't already been shown that we can do it. So the part that was rocket science was the AI model, and that part, we think is in good shape.
Of these four, which do you think is going to be the hardest or the least predictable in the coming years?
So ironically, if you'd asked me that question a year and a half ago when we started, I would have said it's, is there enough demand for this kind of automation, and can the AI model handle those tasks? And both of those, it turns out, we've gotten tremendous validation on right now, both by the customer engagements we've had and the results we've seen with these AI models. The part that I wouldn't have listed high on the list is the software that pulls it all together. This is like old school software engineering.
Yeah.
And it turns out that there's a lot of work to be done there, because this thing can't just be a research prototype where you have 2-3 computers that are being fired up and their command line interfaces to run them and so on. All this has to be done in kind of a push button way, where you've got one button and you say go and the model runs. So there's work to be done there, but again, that's software engineering of the type that has been done for years.
Yeah. You're one of the few founders in physical AI that has scaled through many different cycles.
Yeah.
And understood how to take the concept phase all the way through commercialization.
Yeah.
So for the first time founders listening, some of the ones that we've backed in our portfolio that are building in this new world of physical AI, what are most founders, do you think, overweighting versus underweighting when they're building in today's world?
Yeah. Let me answer this question this way. I think there are probably two pieces of advice I'd give your founders. The first is to focus on the same four things that I always talk about, which may seem obvious, but a lot of founders don't pay enough attention to every one of them, and they all have to be there. And these things are not invented, they're discovered. You have to find an opportunity that has these four things. And those four things, of course, is one is there has to be a really big unsolved problem. If you don't have a big unsolved problem, you can't build a great company, in my view. Two is you have to have a differentiated technology. If you're a commodity doing what everybody else is doing, then you're going to be in a commodity business with margins of a commodity, and that's not a fun place to be. Third, you need an exceptional team. If you're trying to be a world-class product, there's a lot of smart people in the world you're competing against, and you better have a team that's every bit as good as any other team that can be assembled in the world. And the final thing is you want early customer validation, particularly for deep tech. You need to really get customers engaged early, because deep tech requires a lot of investment in capital and team building and so on. And you don't want to do that without the confidence that if you build it, they will indeed come.
Yeah.
And you look for, I look for customers that say, not just this is interesting, but this is so interesting that if you guys could build this, I want to help you get it to market. How do I help you, right? And the second point I'd make is this idea of being contrarian and right.
Okay.
Right. So, you want to be contrarian because if you're conventional, then the value is already priced in, and even if you're right, there's not a lot of value creation to be had. But if you're contrarian and wrong, you're still wrong. So how do you ensure you're contrarian and right? And I think there the key is you really need to think of your startup as simply a collection of hypotheses. Do not start drinking your own Kool-Aid. Realize that the whole idea you have is just a bunch of hypotheses, and think of your job as being a key risk officer, where you literally just list out the key hypotheses in order of risk, and you attack them one at a time and try to de-risk the opportunity. And if you can, basically, as you de-risk those hypotheses, value will accrue. And over time, as you raise, funding, you can just point to all the different risks that you've de-risked with your validation experiments, and get a higher and higher valuation.
One of the things that we didn't talk about, I think, enough is the gap between those that can have these solutions and those that cannot. And so, one of the founders we had on the show recently runs one of the largest robotic fleets, focused primarily on deployment and manufacturing. And what he told me is less than 10% of factories in America currently have robotic solutions.
Yeah.
Many more want them.
Yeah.
But there is this massive gap of, want, but actually can implement.
Yeah.
How does Rhoda help solve that problem, or is that not a problem you're concerned with today?
No, it's an excellent question. Deploying robots today does require a lot more than the robot itself. There's a whole infrastructure that you need to put in place. But this is exactly what we're trying to do. This is why we're saying we're going after generalist robots. The idea of a generalist robot is you can pretty much wheel it in and it can do the task with 10 to 20 hours of training. You don't need a lot more infrastructure. You don't need to build mechatronic systems like conveyor belts and so on and so forth around the robot. The robot can work in the same environment that humans are already working. It's got a similar embodiment to humans, and very importantly, it's got a similar capability in terms of its brain that humans have. And so with that, you can really directly attack this problem and not need a lot of infrastructure around the robot and focus really on the actual use case itself.
So said another way, the deployment challenge is that it takes so long to actually make the thing useful that you're actually getting fewer and fewer people adopting because they don't have the patience for it.
Precisely.
Right.
Yeah. Another way to think about it is that the more specialized your robot is, the more infrastructure is required to run it.
Yeah.
And the more generalist it is, the easier it is to roll it out.
Yeah. Can we close on the form factor and kind of where you see this going in the future? So humanoids is obviously a big piece of the conversation.
Yeah.
You've got some naysayers that say, hey, why do we need these things to have feet? Why not wheels? Why not 6 arms and some other form factor? What's the future you're building for?
Yeah, so it's a good question. So we do not have a fixation on the humanoid form for its own sake, right? Our focus is on solving real problems that our customers have. It just turns out that many of these use cases are being addressed by humans today. So the environments, the objects, the whole setups are built for humans. So if you're building a machine that's addressing these use cases, you likely will need, for example, 7 degree of freedom arms to be able to manipulate these objects and so on and so forth. You'll need a vision system like we have. You need some kind of place to run the brain, the compute and so on. And it starts to look a bit humanoid. Now, one thing we do not need in our environment today, at least, is legs. And so we're not building legs. We're building robots that run on wheelbases because our environments already have AMRs and AGVs that run around. So wheelbase is perfectly adequate to meet the need. In fact, legs can be a bit of an issue because if you have to e-stop the robot, which is a requirement for manufacturing safety, a robot on legs is going to collapse and either damage itself or worse, injure a human being. So in that sense, we're not chasing the humanoid form for its own sake. That actually relaxes a lot of the design constraints around this robot. So for example, our actuators are sized to lift a useful amount of weight on the order of 25 kilograms, not just to look humanoid. So we don't have our robots will not look, like a human being in a suit.
Slender and sleek.
Exactly, because we don't care about that. Our customers are not saying we're going to buy the most slender robot, right? They want to buy the most useful robot. We're selling to businesses where it's an economic analysis. It's not about I want a robot in my house that looks good. So I'll summarize by saying that our robots look humanoid because that's the most functional form to build a generalist machine. But they will not conform to human dimensions purely for the sake of appearances.
Yeah. So I'd love to close with you on the year ahead. You just announced this major capital raise, brought on some great investors, ourselves as a small part of it. What does the year ahead look like for Rhoda? We're having this conversation.
It's an incredibly exciting year. We haven't publicly talked about what our plans are for the year, but I can say that we've talked about the fact that we have multiple customer POCs that have already been successful in the field, and the next logical step that anybody can assume is then to convert those POCs into real deployments and real revenue. And that's something that we're really excited about. We think that, if you look at the hierarchy of what robot development efforts have done over the years, there are a lot of people that have made robots work in a lab setting, and then nothing more beyond that. There are some people that have taken robots into the field and done some kind of field testing, like a POC. And there's very few people that have gone from POCs into actual deployment. And we're now at the phase where that's really our main goal. And if we can succeed at that goal, we think we're on track to change the world.
Yeah. Well, I'm so excited for it, not just as an investor, but somebody who sees the massive labor shortages and opportunities that we have across so many industries, manufacturing, logistics, supply chain, just operations across the world. And I'm excited that Rhoda is leading the way and helping make this deployment that much easier and that much more of a no-brainer for these customers.
Jay, pleasure talking to you. You obviously have a deep understanding of robotics, which is always it's always very nice to see that, and look forward to following your other investments as well. So,
Thank you very much for being here.
thanks, Jay. Take care. Okay.